Hi sir, I'm Dan Changfaran, student ID 03697993. We're from section 2, group 8. The work distribution is as followed. I have done background of project and classification. Chai Hang has done clustering and anomaly detection, and Ayan Said Mohammed has done regression and conclusion. The objective can be seen to 4 parts, which is classification, clustering, anomaly detection, and regression, as there is 4 problem statements. So the goal for classification is to identify key factors influencing fentanyl involvement using demographic and injury data, which provides insight into which features hold the most significance using random forest classifier. Beyond classification, agglomerative clustering was implemented to uncover hidden patterns in high-risk drug combination, revealing insight into dangerous substance pairing and their overlapping interactions. Knowing that, an anomaly detection model was applied to identify abnormal locations with unusually high drug overdose rates using local outlet factors and to aid in targeted intervention strategy. Lastly, prediction of death location based on injury location using a random forest regression model while analyzing geographic patterns to identify high-risk area and show that injury location are often correlated to the death location. That's all for the objective, and now move on to the Python codes. So now I'll be talking about the Python code. All the codes here are pre-run, as the grid search will take too much time exceeding the presentation video limit. Python offers an ecosystem of libraries to enable data extraction, processing, analysis, and visualization. Some key libraries that are used in the project are Pandas for data manipulation and analysis, providing data structures like data frame and series, NumPy for numerical computing, supporting multidimensional arrays and mathematical operation, sklearn, a comprehensive library for machine learning, offering tools for classification, regression, clustering, model evaluation, and many more. Matplotlib, a visualization library for creating static, animated, and interactive plots. Seaborn is built on Matplotlib. It simplifies the creation of aesthetic and pleasing statistical visualization. SciPy provides advanced mathematical function and is widely used for statistical analysis. The data set is first imported into the Google Colab with a condition keep default null as false, as the data has value as string called none. By setting it to false, it will not automatically change it to none. The first pre-processing step is to convert other opioid and other column to binary, as these two columns hold multiple distinct values in the form of string. So this code, you take all the strings that are not called none and convert it to 1, while the strings that are called none will be converted to 0. The next pre-processing is encoding all the categorical features into numeric. But the columns like death city, injury city, numeric county, injury county, injury state, and injury place are done so that it will not affect the value in the data frame, as they are not stored directly into the dataset, but to a variable, as we need the original value for visualization later for better readability. Finally, we drop all the unused column for better computational efficiency. The dataset will be then exported as a physical copy and serve as a record. Now I'll move to the first problem, which is the application of random forest classifier to classify the fentanyl's involvement between demographic and injury data. We first do feature selection, where X are all the feature of all demographic and injury data, and Y is the target variable, which is fentanyl. This step is to assign the problem's condition into the model in terms of X and Y. We then split the data into training and test set with 70-30 method, as 70% is training and 30% is testing. This is done so that there are enough training to obtain a good result. Additionally, this step also determines how well the model performs on new data depending on its training and testing. The feature selection will be then scaled using standard scaler. This ensures that the feature have standard scales across all values for the better processing and prediction of the model. Once the pre-processing of the model is done, we use grid search to find the optimal parameter and fit it in the model. This step is crucial in finding and fitting the best model and ensuring the performance is at its peak. When grid search has been done, this part of code, best CLF equals grid search dot best estimator will search for the best parameter and assign to best CLF variable. The way that is searched the best parameter is using the best estimator function. This is done as the later part will need to call the model by using this variable for prediction. Now, moving forward from this is the prediction. The prediction will be done using best CLF as it has the best parameter of the model. The prediction phase is used for performance evaluation, and the predict proba, which is predict probability, which is for the ROC curve and ROC AUC score. After that, we'll be doing the performance evaluation. For the performance evaluation, we have done best hyperparameter, cross-validation performance, test set performance, classification report, confusion matrix, ROC AUC performance. So from the result, we see that the best hyperparameters are class weight at balance to address class imbalances, max depth F20 to control tree depth and prevent overfitting, max feature with square root to enhance feature randomness, mean sample split at 10 to improve generalization, and number of estimator at 300 for a robust ensemble of trees. The next is cross-validation performance. The cross-validation performance shows that during the 5-0 cross-validation, the model delivered consistent performance with balanced accuracy, scores ranging from 0.8 to 0.84 and a mean balance accuracy of 0.83, reflecting strong reliability across multiple data splits. While the test set performance achieved an accuracy score of 0.85 and a balanced accuracy of 0.83, confirming its ability to predict both majority and multi-classes effectively. Next is the classification report, where it reviews strong results for both classes. As you can see, for class 0, it has a precision of 0.77 and a recall of 0.78, and class 1 has a precision of 0.89 and recall of 0.88. Both results are very high and can be considered as strong. Note that it shows that the matrix does not favor any classes and is very balanced. Next part is the confusion matrix, which shows 937 true negative and 2,108 true positive, with a manageable number of misclassification at 263 false positive and 287 false negative. Next is the ROC AUC performance, which attained 0.91 score, which highlight excellent modern performance in distinguishing between positive and negative cases, while the plotted false positive rate FPR and the negative and the true positive rate TPR curve reflects this strong ability to separate the classes. Now moving to the first visualization, which is the confusion matrix. It further proved the claim that the evaluation out of 1,200 actual class 0 instances has 937 correctly classified, while 263 were misclassified as class 1. While in class 1 situation, the model correctly predicted 2,108 true positive out of 2,395 cases, and 287 misclassified as class 0. This demonstrates that while the model performs well, there's still room to improve its detection of negative cases. Furthermore, since this visual is a heat map, it shows the significance by the shade color, like how dark it is. As the darker the shade is, the more significant the value. As you can see, the true positive has the darker shade, followed by true negative with a lighter shade. showing their significance and slightly lower significance, while the false positive and false negative has either no shade or very light shade, showing their insignificance. Now we'll be moving on to the next visual, which is ROC and AUC curve, which also supports the strong result of the ROC-AUC score at 0.91, as the blue curve here is highly curved towards the top left. As the closer this curve is to the top left corner, the better the model is at distinguishing between the classes, while the dashed line at the middle here serves as the baseline of 0.5, meaning that the random classifier has no predictive power, or the model is just blindly guessing. And moving on to the last feature, which is the feature importance, which shows that cause of death and description of injury contributed the most to the model's decision, followed by age and other human condition, which has a bit of role in it, while race and sex and ethnicity has bare minimum implication to the model's decision. This summarizes that injury data is more significant compared to demographic data when determining the fentanyl's involvement. Overall, this result of the model highlight the model's strong performance in identifying key risk factors for drug-related death. The combination of high accuracy, robust feature insight, and strong ROC performance make this model a valuable tool for identifying patterns and informing preventive measures for the entire problem, which is fentanyl involvement. That's all for my part, and I'll pass it to Chai Hang for clustering and anomaly detection.
Hi, my name is Chia Yi Han with student ID 0369785. Right now, I'll be talking about the second and third data mining techniques used in our assignment. Let's begin with clustering. Our second problem statement is agglomerative clustering of high-risk drug combinations. The first step was feature selection, which I based on the problem of clustering drug types to identify high-risk combinations. I created a list called drug types that includes substances like heroin, cocaine, fentanyl, and many others, basically all the drug-related features in the dataset. This list was used to form the feature variable from the line x equal to df drug types, ensuring that I'm only working with the relevant drug data for this task. This step is really important because it keeps the analysis focused on drug types, which is exactly what the problem statement asks for. After that, I scale the features using standard scaler from scikit-learn. Scaling makes sure all features are on the same scale by transforming them into a distribution with a mean of 0 and a standard deviation of 1. This is key because clustering algorithms can get skewed if some features have much larger ranges than others. I chose standard scaler over other methods like min-max scaler because it handles outlier better, which is common in drug use data, especially with polydrug users. This ensures that clustering results are more accurate. Next, I move on to clustering using agglomerative clustering with 6 clusters. I chose the number of clusters by looking at a dendrogram, which is a visualization that shows how data points come together. The dendrogram plots data points on the x-axis and the merging distances on the y-axis. I noticed big jumps in distance around 15 to 20, which suggested that cutting the tree at that point would give me 6 natural clusters. This visual helped confirm my choice of 6 clusters as it showed clear groupings in the data based on drug use patterns. In the clustering setup, I used n cluster equal to 6 and linkage equal to complete. The complete linkage means the algorithm measures the maximum distance between points in 2 clusters when deciding to merge them. This is a conservative approach that works well for these datasets because drug use patterns can overlap and I wanted to avoid chaining effects where clusters grow too quickly. Hierarchical clustering like agglomerative clustering is great for this task because it lets me explore different cluster counts and see the process through visuals like the dendrogram, which helps interpret complex drug interaction. Alright, to see what the cluster looked like, I created a TSNE plot which reduces the data into a 2D space for visualization. The plot shows 6 distinct clusters, each with a different color. There's a large purple cluster which has the most data points, suggesting it's a common drug combination pattern. Then there's a smaller blue cluster and others in yellow, green, orange, and red, which are more unique groups. This separation tells me the clustering worked well to group similar drug combinations together. To back this up, I look at the silhouette score plot, which shows how well each data point fits in this cluster. Most bars are in between 0.4 and 0.5, close to the average silhouette score of 0.531, meaning the points are well placed in their clusters. The performance metrics also supports this. A silhouette score of 0.531, meaning the points are well placed in their clusters. It shows good separation and cohesion. The Davis-Bode index of 0.731 indicates reasonable distinction between clusters, and the Kalinske-Haraba's index of 563.990 is high, pointing to tight and clear groups. Together, these metrics are visuals, and visuals confirm that 6 clusters are a good fit for the data. Alright, next. Moving into anomaly detection, our third problem statement is local outlier factor to identifying high-risk locations for unusual death patterns. For anomaly detection, I shifted my focus to location-based death patterns to find unusual hotspots. I selected features like death city, death county, and death state to group the data by location. Then I counted the number of deaths for each location, creating a death count column. And this step is crucial because it prepares the data for anomaly detection by giving me a clear picture of death counts across different geographic areas. It allows me to analyze the patterns at a location level, which is different from the drug-focused clustering I did earlier, and helps me to connect the dots between drug combinations and their impact in specific areas. Okay, using the local outlier factor model, I identified 13 locations with unusual death counts, and they are all in CT. Hartford stands out with 1,930 deaths, which is a huge number. Waterbury follows with 898, and Bridgeport has 997. Other locations range down to 221 deaths, but all are much higher than typical counts in the dataset. These numbers suggest these areas have abnormal death patterns, possibly linked to the high-risk drug combinations I found in the clustering step. The fact that all 13 locations are in CT is interesting. It might point to a regional factor that's causing these unusual patterns. The combined box plot and scatter plot really brings these anomalies to life. The box plot shows the distribution of death counts by county, and most counties have low counts, with medians near zero and small ranges. But the red X markers for the anomalies, like Hartford at 1,750 and New Haven around 1,000, stand out far above the whiskers. This visual confirms that these locations are extreme cases, way outside the usual distribution, and it highlights just how significant these outliers are compared to the norm. These outliers are important because they show areas where death patterns are unusually high, which could be tied to a risky combination, the drug combination that I identified. The concentration in CT might suggest a regional issue, like a specific supply or usage trend in that area. Hartford, with its extremely high count, is a clear priority for further investigation, and is a hotspot that needs attention to understand what's driving these numbers. Right, that's all for my part. I will now pass it to Ayan for the next part. Thank you.
Hello, Ayan here, student ID 0363399, and here I'm going to talk about the random forest regressive model, which requires a well-defined feature set and target variable. And in this case, we have test city, which is going to serve as the target variable y, while the injury city, injury country, injury state, injury place will make up the feature set x, representing the location where the injury took place. This step is crucial in framing the problem. Overall, the goal is to assess the relationship between injury location and injury and dislocation to determine if injury-related factors can effectively predict the place of death. And in this part of the code, and it's useful for splitting the dataset into training and testing sets to ensure the model is trained effectively and evaluated accurately. Here we have test size which is equal to 0.3, meaning that the 30% of this dataset is going to be used for testing, and the remaining 70% is for training. And this ratio provides the model with enough data to learn meaningful patterns while keeping a portion aside for unbiased performance. And here we have random state, which is equal to 42. That ensures the split remains consistent across multiple executions, leading to comparable results. After the splitting, the feature will then be scaled using a standard scaler, and this ensures that the feature have standard scales for better processing and prediction of the model. And in this part of the code, it performs grid search CFE to optimize model performance by finding the best combinations of hyperparameters, and it defines this parameter grid, which contains n estimators, max depths, mean samples, and split and mean sample leaf. And also, then the grid search stands up with the cross-validation CFE, which is equals to 5, using negative mean squared error and as the valuation metric, and then anchovies, which is equals to -1, to utilize all CPU cores for efficiency. Finally, the model is trained with grid search.fit and to determine the optimal settings. And then after that, we have this part of the code, which is used to retrieve the best performing model found during the grid and search CFE process. And this uses grid search.best estimator, which allows access to this optimized model, which can then be used for making predictions on new data or further analysis. And then we have this part of the code, which is responsible for making predictions on new or unseen data. Then the predicted values can then be compared with the actual target values to evaluate the model's accuracy and effectiveness. And in this section of the code, performance was evaluated by analyzing cross-validation results, and the MSE records and scores from cross-validations are calculated. It typically returns negative values, so the code converts it back to positive for better interpretation. And the cross-validation scores, we have it here, is are 877.15, 861.14, 978.03, 956.51, 850.69, and the mean is 904.70, highlighting that the model has consistent performance. And this step was performed to evaluate the generalization of unseen data to help in preventing overfitting from occurring. Additionally, the best hypermeters were displayed, which shows the max depth is 10, mean sample leaf is 4, mean sample in split is 10, and n estimator is 100. Moving to the test and set performance, it shows that the MC score is 901.0.22, indicating regular squared prediction errors, and also mean squared error, which shows mean absolute error, which shows 15.04, and suggested that average deviation of 15 units from actual values. Also, we have relative mean absolute error, which shows 13.30%, which highlights a relatively low error percentage. And then we have root mean squared error, which is 30.02, which provides a clear measure in the original unit. And then lastly, we have R squared, which is 0.77, which explains that 77% of the target's variancy and demonstrating strong predictive ability to reflect the model's ability to capture the patterns of the data. And here we have the scatter plot and shows the performance of the actual values of death and against the predicted values to assess how well the model predictions align with the true values. And there is this red and diagonal line which shows the perfect fit, and which is where the predicted values exactly match the actual values. Additionally, we see here that some points is lie far from and far above from the line, and some lie far below, which means that maybe the model may either overestimated or underestimated the actual values. And here we have future importance, and this part illustrates how significantly different features contribute to the predictive model. And the most dominant one is the intricacy, which has importance score close to 0.9, towering over the other features. And it indicates that the model heavily relies on the city where an injury occurred and when making predictions. On the other hand, we have injury place, and which has lower score, nearly 0.05, and then we have injury country, which shows smaller contribution, which is score close to 0.01. And then lastly, we have injury state that has the least score, nearly 0.00. And this imbalance in future imbalance in future importance suggests that the model finds the city level data far more informative than geographic levels like country and state, and possibly because cities capture more localized risk factors and environmental conditions that impact injuries. And here, to summarize all, we have all the machine learning models applied has effectively addressed the objectives where the random forest classifier model achieved 83.05% accuracy and a 91.13% ROC AUC score, proving its reliability in distinguishing fatal-related cases, and with injury data like cause of death identified as the most influential factor. And while the agglomerative clustering model successfully repeated high-risk drug combinations and overlapping clusters, uncovering complex drug interactions and results of moderate to strong performance. Meanwhile, local outlier factor model effectively detected high-risk locations for unusual drug overdose deaths. And these findings is in highlighted specific cities with significantly high death rates, such as New Haven, and so on. And lastly, the random forest register model achieved an R-squared score of 77% with low error matrix of 15.04, .05, and RMSE, which is equals to 30.02, and confirmed that injury city was strongly correlated with death city, emphasizing key areas for further investigation. Overall, all models successfully met their respective objectives and providing insights on their problems. And that's all for our assignment presentation group, our group assignment. So thank you.